So in the last video, we finally expanded our kind of notion of acidity and basicity to non-aqueous solvents, right? But if you notice, we were always talking about solvents that are aprotic solvents. This is that they have protons to give and protons to gain. So proton transfer can happen, right? Because we always talk about this auto protolysis that happens in these solvents. These non-aqueous solvents like ammonia, they can still be NH4 plus, right? Or make NH2 minus, right, from NH3 ammonia. That would be one example. So this definition of acidity and basicity did get us into the non-aqueous realm, but we didn't get into aprotic solvents. So these are solvents where you don't have any protons that can be gained or lost like that. And so this requires a different definition, and we're just going to talk very briefly about it. It's called the solvent system definition. And so this allows you to extend the concepts of acidity and basicity to aprotic solvents. We know that protons are not required to have acids or bases in them, right? According to the Lewis acid and Lewis base definitions, Lewis acid just accepts electrons and a Lewis base just donates an electron pair. It doesn't have to do anything with protons necessarily. So autoprotolysis of water, just to remind you, right, 2 molecules of water going to hydronium and hydroxide. Now let's expand this and just call it autoionization, okay? We're not necessarily talking about protons here. Think, for example, this example, bromine trifluoride. This can undergo autoionization associated with the fluoride. So you can get 2 molecules of bromine trifluoride giving you 1 molecule of BRF2 plus and 1 molecule of BRF4 minus. So fluorides are hopping around here. So the definition here is any compound that increases the autoionized cation is an acid, okay? And so any compound that increases the autoionized anion is a base. So here is the anion. So any compound that increases BRF4 minus in BRF3 solvent, BRF3 is a liquid, by the way, would be a base. And any compound that increases the cation, autoionized cation, in this case BRF2 plus, would be an acid. And so, if you have this salt, BRF2 plus with AsF6 minus, these are pretty exotic, guys, but it's okay. This would be an acid. Why? Because when this dissolves, it's going to make AsF6 minus and BRF2 plus. Well, BRF2 plus is the autoionized cation, so this would be an acid. KBrF4 would be a base. Why? Well, this is going to dissolve. It's an ionic compound at K plus and BRF4 minus, thus increasing the concentration of the autoionized anion. So that's the definition of the base in this sort of nomenclature. All right, so that's just a little bit of a teaser on, aprotic solvents. You can have acids and bases in them, definitely. They do play some important roles, particularly in inorganic synthesis and so-called superacids and superbases. Superacids are your book mentions about it, but basically are just any acid that has a pKa less than 0. So anything that can go outside of water. And there's some exotic examples of those. And a superbase is pKa greater than 14. But the specifics there, I'm not really too worried about you knowing.